Okay, thanks a lot. I thought this workshop format would be a good opportunity uh, to share some ideas that I've been working on really recently with Loic Nessif-Lachapelle, who's an undergrad at the University of Toronto. I think there are a number of interesting theoretical questions to pursue related to this, and what I want to convince you of is that I think they should have important observational consequences for the field of direct imaging. Okay, so we start with sort of the big picture. Imagine we're trying to look at the solar system, but we place it 10 parsecs away from us. Okay, so here's the black body spectrum of the sun peeking in the optical. And now we ask, how hard would it be to see the Earth, right? So turns out that only about 1 in 10 billion photons that leaves the sun scatters off the Earth to come towards us. So you need an instrument that's capable of achieving a contrast ratio of 10 to the 10. Right, so that's what Habex and Louvois are aiming to do. So you can get a spectrum of a Earth analog atmosphere. Right, but that's going to happen in the late 2030s. So that's a challenge. If you want to do something a bit sooner, well, you could say, well, I don't want to go after an Earth. Let's go after a giant planet that's 10 times bigger. So you have 100 times bigger fluxes. So that contrast ratio of 10 to the 8 is actually about the goal that for the next generation of direct imaging instruments that would go on the ELTs. It's what Hannah mentioned as the sort of goal for W first if it flies with a coronagraph. But where we are today is that the state-of-the-art instruments, GPI and Sphere, can achieve contrast somewhere between 10 to the 5 to 10 to the minus 6. Right, so that is a spectacular technical achievement. You're pulling out a 1 in a million signal. Okay, it's not enough to see the scattered light off any size planet, but of course, the idea is that you can go after the monsters, right? The super Jupiters while they're still young. For example, a 5 Jupiter mass planet at 30 million years can approach temperatures of up to 1,000 Kelvin just from the heat of accretion. And that black body emission at longer wavelengths is much brighter, right? Right. So that's led to a number of spectacular detections, right? Some of the most iconic systems like HR 8799, Beta Pic B. But of course, the punchline has been that these super Jupiters are rare, right? There are not many of these. They occur only around about 1% of stars on average. But what got me interested in this is, this D-Sharp survey that's already showed up several times, which suggests that planets are not rare. It's just that they're lower mass, right? So Zhang et al. With the D-Sharp team, by analyzing the gap widths, estimate masses for planets that would be needed to open these gaps somewhere between Neptune and Jupiter. And that seems to be consistent with what microlensing has found closer in, just that there are many more Neptunes than there are Jupiters and super Jupiters. Okay, so if that's true, then that's terrible luck, right? You put all this sweat and tears into direct imaging so that you can get to this point, but you only get to the point where you're just above where all the planets are sitting. So you might say, well, these direct imaging people, they just need to roll up their sleeves and go into the lab, and if they just get their contrast down by a factor of a few, they'll start finding all of these. But that's actually not the case. If you look at how these contrast ratios are going to depend on planetary mass, it's really, really steep, right? So as you go from, say, a 3 Jupiter mass planet to a Saturn mass planet, the contrast drops by something like a factor of 10 to the 5. And the reason for that is simple to understand. Here's our 5 Jupiter mass planet at 30 million years. And GPI is observing here at 1.6 microns in the H band. You can't really go to longer wavelengths because the atmosphere gets in the way, and you're on the wrong side of this black body curve. You're on the side that drops exponentially. Okay, so If you imagine dropping the mass of this planet so that the temperature goes down, then your black body is going to go down, but more importantly, it's going to shift to the right, and that makes your flux drop, off a cliff. Okay, so the first big takeaway, the point that I want to make, is that even if the occurrence rate of planets rises smoothly from super Jupiters all the way to Neptunes, the distribution of contrast ratios does not. Okay, thermal emission is only going to help you for the very monsters that are in the tail of the distribution, but beyond that, you have to rely on just the scattered light. Okay, so the big picture is that going forward, if you're just looking for planets, you're going to be stuck at sort of the 1% level. You have to observe hundreds of stars to find just a few, and that would continue even as you keep improving your instruments down to contrast of 10 to the minus 8, and it's only down here at Habex and Louvois that you start finding lots of planets. Okay, so that, I think, is a multi-billion-dollar problem, right? Habex and Louvois, happening in the late 2030s, need a lot of technological development to be able to do that, right? And we really are going to need to find some science targets sort of in this space so that we can keep finding things and getting observing nights on the biggest telescopes in the world as we improve instruments going down towards those goals. Okay, and I think the solar system actually gives us a really good idea for how we might be able to do that. Okay, so we said that thermal emission is not going to help us as we go down to lower mass planets, so we need to find these planets in scattered light. And the best way to do that is by increasing the scattering surface area. Okay, so this is the Saturnian system in a way that you probably haven't seen it before. Saturn and its spectacular rings are this central white pixel. Okay, and then every moon that you've heard of, like Enceladus and Titan, those are all inside this red orbit of Iapetus here. Okay, they're all nicely on circular coplanar orbits. They formed in a gaseous circumplanetary disk. But outside of that is a huge mess of inclined, mutually crossing, eccentric orbits, which are the irregular satellites. These are small dark moons that are the leftover planetesimals that didn't get incorporated, and they've been colliding with each other for the age of the solar system. Okay, so these planetesimals would have been perfectly happy in circumstellar space, but then you pack them into this small Hill sphere, and it's just like it's a grinder, right? What we see today are just the dregs that are left over from that process. The irregular satellites are the most collisionally evolved population in the solar system. Okay, so the point is that at early times, these would have generated spectacularly bright circumplanetary debris disks. And we see these populations around each of the 4 giant planets in our own solar system. Okay, so we've been trying to understand these a bit better, analyze their collisional evolution quantitatively, and understand the main effects that are driving their evolution, just in order to think about what are the best environments in which we might be able to find these. So LOIC has implemented a model that was put together by Kennedy and Wyatt in 2011. What it does is it evolves a particle size distribution in orbit around a planet, and it models that collisional cascade, estimating collisional timescales just with a particle in a box formalism. And to sort of give you the sort of big picture physical intuition, I've already said that the planet's thermal emission has a really steep mass dependence. As you vary the planet's mass, these irregular satellite disks are almost flat. Okay, so how bright they are, how big your contrast ratio is, goes up and down depending on what your initial mass budget is in irregular satellites, but it almost doesn't depend on what your planetary mass is. And that's just for simple reasons. They're competing effects that end up mostly canceling, right? So as you increase your planet mass, you're making your dynamical timescale faster. So that's making collisions happen faster and faster. So that's going to cause you to grind down and be fainter. At the same time, as you increase the planet mass, your Hill sphere grows. So your particles have to explore a larger volume before they find one another and collide. That increases your collisional timescale. And those competing effects, for the most part, end up canceling. The other place that you gain is in time, right? So planets cool, and then you have the same problem. As you cool, then your thermal emission drops off a cliff. By contrast, these debris disks, what they want to do is they want to evolve into a state where the collision time between the largest particles is comparable to the system's age. So they decay as 1 over time. Okay, so they decay much more gradually as you move forward in time. Okay, it's probably a good moment to take a step back and talk about sort of 2 different types of circumplanetary disks. I don't even know what to call these things. Right, so they're definitely around a planet. They're circumplanetary, but we've already had talks about gaseous circumplanetary disks. We're going to hear more about those tomorrow. But they're sort of very different beasts, right? So these disks, they're much hotter and they're much brighter. These makes them very appealing, for looking for them observationally. One challenge is that in this case, you have to compete with the bright circumstellar disk around it. So that's one challenge. I guess you'd also like to be able to resolve the gap so that you can see the planet and separate it from the disk. Right, and then they last for a few million years and then they're gone. In some sense, maybe this helps because then you know which systems to go after, the ones that have disks. By contrast, these irregular satellite disks, they live far beyond the gas disk lifetime. They can live for billions of years. And because of that, then the only thing that you're competing with, well, the only thing is the star. And it sort of also eases some of the resolution problems in that you only need to resolve the planet orbit. It doesn't matter if you resolve the planet's Hill sphere or not. Okay, so keeping with astronomical tradition, we should probably pick some ridiculous name for these, like ultra long-lived circumplanetary disks, or. Okay. Okay. Yeah. I would love to take suggestions. Then I can blame you later. Yeah. Okay, so we've been trying to think about what would be the best type of target star to look for these types of objects. So the first thing is you really want to look around low mass stars, right? That's because low luminosities and weak radiation pressures means that you can have much smaller particle sizes. So that means that for the same mass budget in irregular satellites, you'll have a lot more scattering surface area for a planet around an M star than a planet around an A star. You can also ask, where should your planet be so that you're able to find these better? Well, typically, if you're looking at scattering, what you want is you want to put your object as close to the star as possible so that it intercepts a large fraction of the starlight. Okay? In this case, you actually get a turnover. So at large distances, it does fall off like as an inverse square law. But as you bring your planet inwards, again, those dynamical timescales are getting faster. And at some point, you just end up grinding your disk all the way to nothing by the time that you're actually looking to try and find them. Okay, so there's some optimum here, which corresponds to asking, at what semi-major axis will the collisional timescale of the largest bodies in your collisional cascade match the age at which you're actually observing? And that scale depends on different parameters, but reasonable values are somewhere between 5 and 30 AU. So that's where our giant planets are, so that makes it interesting. And it's far enough that you don't have much problem in resolution trying to separate that from the star. Okay, but the biggest uncertainty in all of this is in what is your initial mass budget in irregular satellites. And I would say that we don't actually even know how these objects get captured. Okay, so most of the recent literature, has been all in the context of the solar system and perhaps biased by the NICE model. The focus has been on whether you would be able to capture these during a late dynamical instability as planets are encountering one another way after the gas goes away. So I was sort of complaining about this to Scott Tremaine and saying that this would be an interesting problem to work on because I think it would have important observational consequences. And after a couple seconds of looking at me, he says, no, I don't think that's the interesting question. So it's like, okay, blew that one, I guess. But he did pick up. He said, I think the interesting question is actually how do you get rid of all this material, right? Because the natural time to pick all of this up is during the gas phase where you have tons of solids around and you have dissipation. Right, so, we know that giant planets need to have access to of order 10 Earth masses of material, right? So then the question is, we know that most of those solids are going to get into the planet, but at what level is that accretion complete? Like what fraction is left over and put into orbit around the planet? Okay, so is that 10 to the minus 1, 10 to the minus 3, 10 to the minus 5? Okay, so I don't know the answer to that. I think it's a really interesting problem to work on, and I'm interested in it. But I want to convince you that for most reasonable values that you could get, this should be important. Okay, so what we did is we took a population of low mass stars, M dwarfs, and we took a range of ages from the PALM survey, which is a direct imaging survey of lots of nearby M dwarfs. And then we imagine putting irregular satellite disks around each of them. Okay, so let's take maybe a very optimistic first case. Let's say that planet formation is extremely messy. Okay, you have 10% left over in orbit around the planet. You have something like an Earth mass to play with. So first here is the contrast ratios for just the planet itself, right? So now we have semi-major axis in observer units over here. Here's a contrast ratio for Habex and Louvois, ELTs and W first. And here's GPI and sphere, right? So GPI and sphere are detecting the monsters in thermal emission, but most of them are down here at sort of 10 to the minus 10. Okay, at this mass scale in irregular satellites, these things are extremely bright, right? So every one of these planets has a corresponding irregular satellite disk, and it can boost it by several orders of magnitude. And, even though this scale is optimistic, is not crazy. And I think the fact that this is actually detectable today motivates maybe going after some of the brightest, best targets in the sky and checking. Because if you do find some of these, then I think this has very major implications for your strategies as you move downwards over here. And I think it has interesting implications for planet formation itself. But if we want to be a bit more conservative, we can again look at the solar system. Okay, around Jupiter, Saturn, Uranus. Today, at 5 gigayears, we have something like 10 to the minus 6 Earth masses. Okay, and we've said that these debris disks, the contrast ratio on the masses, should drop as 1 over time. Okay, so if you capture these at 5 million years, these should be 1,000 times bigger. You're something like 10 to the minus 3 Earth masses. Okay, from another angle, you could ask, okay, well, how much solids are in the regular satellites, the ones that form in the gaseous disk? And that's a few percent of an Earth mass, which is, almost certainly a lower bound for how much mass you had in solids in that proto-satellite disk. Um, so these are sort of mass scales that we can compare against. If we try that one, if we try sort of a percent of an Earth mass, these irregular satellite disks are still extremely bright. These would be trivial to find with the next generation of ELTs. And even if we go beyond 10 to the minus 3 to, say, a pessimistic 10 to the minus 4, these disks are still 2 orders of magnitude brighter than the planets. Okay, so I think no matter what, these are going to be important structures to try and understand, because this is what direct imaging is going to find. Okay, so I wanted to close with just a couple implications that I think are interesting to think about. So, the place where I started is, where all this comes from is the fact that Neptunes are much more common than Jupiters and super Jupiters. Right? And we've already talked about how that's sort of a strange thing. It's not clear why we should have ice giants at all, right? If you can get to 15, 20 Earth masses, why don't you run away and become a gas giant? So one of the crucial ingredients in that is that you need to know opacities in these protoplanet atmospheres. So all the dust that you would generate in collisions of these irregulars would help supply some dust and some opacity to those protoplanet atmospheres. It would slow down the cooling and maybe delay the time until these planets would become gas giants. But maybe more importantly, talking to Chris Ormel, he mentioned that in these protoplanet atmospheres, you have some dust opacity, but you have to also worry about the fact that that dust is going to settle in this atmosphere on short timescales. So maybe even more important than the amount is the fact that you would continually resupply this dust to the protoplanet atmosphere and give it a continual source of opacity to delay that cooling. The other more dramatic implication is just dynamical. Okay, if you think about this just in a planetocentric reference frame, you have a planet, you have satellites going around it, and then you have a very massive perturber, aka the star, in orbit around that. Okay, so that's the setup for the Kozai mechanism. You have an outer quadrupole potential. So when you capture all these irregular satellites isotropically, the ones that have inclinations bigger than about 40 degrees, those are going to undergo Kozai oscillations, go to really high eccentricities, and come crashing into the inner system. Okay, so basically, as soon as in that planet formation process, you turn off all the inner precession frequencies that keep the apsides going around, then all your near polar orbits are going to come crashing in. Okay, and in Kozai, you think of timescales that are millions to billions of years. Here, the perturbers, the sun, the timescales are like 1,000 years. So you basically get an instantaneous dump of everything that's on near polar orbits onto the inner satellites and maybe disrupt that first generation of satellites all at once. Right? And if you look today, that's what you see. You see a whole cone of irregular satellites missing around the poles, around each of the giant planets. Okay, so in conclusion, the summary is, well, we're confident now that there should be many more Neptunes than there are Jupiters and super Jupiters. Okay, but even if that trend increases smoothly, the contrast ratios do not, right? Thermal emission helps you find the HR8799s, the monsters at the tail of the distribution, but for the vast majority, you're looking in scattered light. So you really have to go really far down to contrast ratios of order 10 to the minus 8 before you start finding any planets at all. Okay? So it's not all doom and gloom. The main takeaway from this talk is that, even if we investigate a wide range of scales, our clear prediction is that most of the detections from direct imaging going forward are going to be of irregular satellite disks. Okay, so I think that motivates thinking about these a little bit more carefully. Probably the most important question is, this one of how efficient planet formation is and how much can you keep in orbit around the planet as these planets are forming in protoplanetary disks. I've touched on sort of two implications One, would this continual supply of dust help suppress gas giant formation by continually providing opacity as protoplanet atmospheres? And the other is, this could be a very bad day on that first generation of satellites. Maybe you just blow them up and you have to reaccrete them. Yeah. So I would love to talk more about a lot of these things, but I'm happy to take questions. Thanks.
So can we use the fact that GPI and SPHERE haven't detected anything of this sort today to rule out this one Earth mass scenario?
Yeah. I mean, the answer is no, but good question.
Thanks.
Yeah. So that was the first thing. The first thing that we checked. So maybe the one thing that I've sort of gone through quickly is that the contrast ratios that you get really depend on your target sample, right? So the GPI target sample really focuses. A lot of them are A stars because that's where these giant planets has been found. So, but it depends really strongly on that stellar mass. So if you look around A stars, you're not going to find many irregular satellite disks. So this is a sample that's optimized for finding irregular satellite disks. So that's something that we've checked. We've taken the actual GPI sample. We've put irregular satellite disks at 1 Earth mass around all of them, and you don't find any with GPI.
So why does the stellar mass matter for the irregular satellites?
So the biggest effect is that low mass stars have a lot less luminosity. Radiation pressure is much weaker, so you can have much smaller dust particles around planets in those systems. So if you have the same initial mass budget in irregular satellites, you can get much more surface area for a planet around an M star than a planet around an A star. But it also slows down all the dynamical timescales by a smaller factor to be around an M star. Yeah. It's a surprisingly large effect, actually.
Hilka?
Why do you think that you get this collisional cascade and grinding all the way down and not reaccretion of solids into a body in the disk? As you, I'm sure, know, in Jupiter's rings or Saturn's rings, we think it's not a collisional cascade, right? We're not draining the material.
Sure.
Naively, I would expect the velocities are low enough in these disks because it's just around the planet.
Well, so sure. If maybe the picture to pull up is any of the ones. Yeah. So if you're in this pixel, which is where Saturn's rings are, then all the dynamical timescales are so fast that you have so many collisional timescales that you just get into a super flat disk. On the scales of the Hill sphere, the collisions are not frequent enough, so you don't have enough collisions to grind you down to disk to make everything circular and coplanar. So you just continually have collisions. I think an interesting question is, maybe once you have gas, then that's going to help damp you along the way. So I think it is interesting to think about whether you have enough damping from gas to sort of change this picture substantially, in which case you would need something to happen afterwards to excite the orbits of these things, or maybe you need to capture them later. Maybe close encounters between planets at late times, flybys can give you eccentricities. I don't know. So I think that would be interesting, but I don't think it's clear at all that if you start putting these objects filling the entire Hill sphere, that you should expect to collide into a really nice cold disk.
But sorry, maybe I missed something. But I thought you appealed to the collisions to give you enough cross section so you can observationally see it.
Yes.
Right? And so if you do have that, then it's sort of a runaway process, right? Because the smaller bodies will collide even more frequently.
So, sure. So.
And, yeah. So I have a hard time seeing how you don't have collisions frequent enough that you would.
Well, so the collision timescales vary with your particle size. So the collisional evolution, because most of the mass is in the largest particle sizes, then the collisional evolution is driven by the collision of the largest bodies. Those can have long collision timescales. But yeah, as they start colliding, then those get shorter and shorter. So So certainly the smallest particle sizes are colliding frequently, and maybe those get into a nice colder disk. I don't know.
Hey, Phil?
Could you comment on the sort of competition between seeing these disks and then the sort of background of the regular debris disk? Because I guess you know, 5 million years, presumably that would be very bright, but is falling with a steeper or shorter time scale, and so there must be some sweet spot in terms of age where this would be most observable.
Yeah, I think that's an interesting question. I don't think I can give you quantitative numbers. I mean, I guess what I would say is that because the collisional timescales are so short for these for those irregular satellites, when you look for the age of the solar system, then the masses go up by a factor of something like 100,000. For the zodiacal dust, then the collision timescales are longer between the largest bodies. So presumably, the amount of material that you had there was not many orders of magnitude earlier in the past. So I think if you take the current zodiacal light levels, that would not compete with these objects that I'm putting on these plots. But maybe if those were substantially larger, then that would start to be a problem. Yeah.
Man? Jeremy?
Well, I was going to make a comment on Hilke's comment. Seems these. You could help us by reminding us of the typical velocities of these collisions and how those compare to the elastic strengths of the bodies and really just to their melting temperatures.
Sure. So,
well, I mean, the question really is whether, by the time the bodies have dissipated enough of their free energy to get down to a disk, constant angular momentum, they have. Do they survive to that point, or how small are they at that point?
Well, so like in Saturn's rings, the relative velocities are a millimeter a second.
I know, but they may not have started out from this. They may have started out at much smaller relative velocities. They're largely ice particles.
In Saturn's rings?
Yes.
So I'm saying that in Saturn's rings, they're very low, but for these irregular satellites, they're of order the orbital velocities, so that they're enormous.
I would have thought.
Yeah.
Indeed.
Yeah.
So, maybe it never circularizes because the collisions are so destructive.
Oh, I see what you're saying. Yeah, I mean, at some point that that should gradually damp away energy, but yeah, I think any of these collisions between comparable sized bodies are just going to completely disrupt these objects. Yeah.
Okay, last question. How will we tell when we see one of these that it's not a planet?
Yeah, I think that's an interesting question. So for example, one of the nice features of an instrument like GPI is that it also gives you polarization, right? So these irregular satellite disks, they orbit far outside the planetary magnetosphere. They should sort of have similar polarizations to what we see in circumstellar disks, and those can be polarization fractions of something like 20%. And that's way bigger than you get from a planetary atmosphere. So as soon as you find one, you know it's not a planet, and you also know it's not a false positive. It's really easy to detect it. You can detect it in polarization too. Yeah.
Thanks again.
Great, thanks.